mention is discuss the workflow. So the first question is to compute the regression coefficient for fish and cauliflower and use the bootstrap to calculate the 95% confidence rate of the beta 1 and to test by these three methods, percentile, BC, and BZ method to see if the beta is different from 0 or not. So first is from the previous homeworks, that I just import my data and divide a function of the bootstrap. So after doing this, I can get the variable, the matrix of the bootstrap fish and the fish of the cauliflower. And also doing the previous homeworks for bootstrap the beta 1, and you can see the histogram of beta 1 distribution. What's the today's homeworks is I divide a function to get the number of quantile. So the function I get is the quantile, and the x is my data, and the p is your request quantile. So the first I use the source, the function, to rank the data from the smallest to the largest. And we also need to know the end of the length of x to get this index. And this index is stand for the position of the request p. So we can know the position of the p. And what we know is also to know the lower and the upper bound to see the index with its position. And after doing this, I also calculate the weight of these two bounds. And the weight means the upper bound of the weight value. So I finally return this value. The 1 minus weight is the lower bound weight, and it's times the value of the lower, and the weight times the upper bound. So the first method is percentile CL. I transfer my beta 1 variable to the CDF, use this function, the CDF beta 1, and the plot result will see like this. And these two is the result is coding. So how do we calculate the lower limits is based on my function, and this beta 1 is my data, and the p, which is 0.025. So we can get this lower limit is about 0.07, and I use the AB line to see the gray line of this. And the upper is also doing the same again, but change the p to 0.975. So after all, we can get the percentile CI like this.
Can you explain why do you need a weight? What is the weight? Previous.
The weight is, it means this index is between the lower and upper bound. So if the weight is 0.5, it means it's in the middle of these two bounds. But if this weight is the 2.2, it means it's more closely to the lower bound. So I have to put this 1 minus weight to get this weight of the lower bound.
I don't quite follow why you need weight. Because that index is that if you have a total 1000 beta 1, then the index you decided will be the lower bound will be 20 pips, and upper bound 970 pips already. You just need to find another location. Why do you need the result, the lower again? I don't really understand. So the lower is the index, right? And then the index for the sorted x should already be that lower bound. So why do you need to multiply with 1 minus weight? I don't get that.
I see, because I use the ECDF is a continuous distribution. So I try the R is the function of the compound. So it will get the exact number of the function. But it's not necessary.
Yeah, because the output is the beta 1, right? Sorted the beta output is the beta 1, right? Next page. Or next page. So output is beta 1. Right? You don't and then output is beta 1 and then you put a beta 1 here. So you don't, this is just for plot. Right? You don't use this in the calculation after. You need only beta 1. This is only for plot. You didn't really need to convert the beta 1 into some kind of distribution. This is only for the plot. So beta 1 is the it's okay. You get a correct answer, it's okay, but I don't see the need to calculate the weight. It's okay. Go ahead.
So the output of the figures, and the second method is the best correction. So the first thing to do is to see the bias is needed or not. So we need to calculate this G of theta hat is equal to 0.5 or not. So I use this, the theta is the mean of top 1 and going to the G function, and we can see that it's 0.55 is not 0.5 is biased. So follow this formula, we have to know the Z0, and the Z0 is equal to the inverse phi of the G function theta hat. So I do the normalization of my beta 1 to Z score, and to get the phi function, this. So I can calculate my Z0 by also this function, and this is my data of the phi, this is the function, and this value means the G theta hat. So after we got the Z0, we can put it into this formula to get the theta. And again, this is from this formula. So we can see that we get the lower limit and upper limit of the bias correction.
Okay, actually, that's correct. Anyone here? Which part is incorrect? Yeah. Mean, right? So mean, this should not be mean. The theta is not the mean among the beta 1. Theta is the beta 1 calculated from the real data. theta 是你用真正资料算出来的 theta， 不是所有 beta 1。theta 其实就是你用你原本资料算出来的 beta 1， 不是所有的 beta 1的平均。这是 typical mistake. So beta 1. So that's why I say you need to include the beta 1 calculated from your real data as one of your bootstrap. Because you need to find the location of the observed beta 1, whether it's at median or not。我再用中文讲一次哦，你应该要算，你算出来用原本资料得到贝塔 one， 所以我一直强调说，你要把贝塔 one 放在你所有的不选贝塔其中的一个，所以是1加999个贝塔 one， 对吧？因为你这样子把那个放进去之后，从小排到大，你才知道你观测值的贝塔 one 是不是在正中间嘛，是不是在 median 嘛？有听懂吗？ Yes. Okay. So that's so this is not a problem when you use percentile because in the percentile method we don't really care whether that observed the beta one is median or not. However, for bias correction, we need to check whether the observed the beta one is median or not by 50% on quantile. Okay, so you need to include you observe the beta one into all the beta one, and you sort it and you find whether the beta one is the location of beta 1. If you do this, it's almost guaranteed no bias correction is needed because the mean of all the beta 1 almost guaranteed to be in the almost guaranteed to be very close to the median. And therefore, there's almost no need for bias correction. You can see 0 is really small. Okay? Because that's the reason is because you use the mean of the beta 1. If you do this, it's almost guaranteed no bias correction is needed because this is incorrect. Okay? You can fix that before you turn your homework. Question on that is critical. You understand? Yes or no? Yes? Okay. And then if you do this correctly, the calculation, the remaining calculation are correct. Okay? Please.
Sorry about the mistake. And the next is BC acceleration. And the A is followed by the check-back method. So I have to calculate the check-back to the beta 1. And this is from the previous homeworks. So I have the beta 1, the J, and the beta 1 J, and this is the mean of the knife. And the A is followed by the equation of this. So I have to do this to let the mean of the beta 1 knife minus the heavy knife beta 1. And doing this calculation to get the A. So I have a D0, but it's incorrect. But I can put it into this formula to get the theta. So I use the function again to get my lower bound. So after doing this, I can also get the lower limit and upper limit. So compared with the 3 next, I can see that it's slightly movement between among the CI. And the second question is to bootstrap test the significant difference between these two species and do the correction by the PCA. So it's just putting to my data, so get the bootstrap of these two species. And we need to know the difference between two species. So I use the function means to get the aggregate stress means about all species and C species, and to get the difference of the O minus the C. So you can see the histogram of the difference. And again, I use the HCF to transform my data to the scale. So it's incorrect again, but yes, we need to know it's biased or not. and to get the Z0 value. So the observation is followed by the straight line. It's same as the question 1. So after we do the calculation of the A, just like this formula, we can put into the equation to get the lower limit and the upper limit. So we can see that it's contains the 0. So we can conclude that it's no significant difference between the density of the two species. Thanks for the attention.
Okay, thank you. Any question? Maybe we'll go to the next one, then we'll discuss. So please. Right.
Hello everyone, I'm Jack. Something of the I'm Joey Webb. I'm going to make a presentation to explain how I do my homework this week. For the first question, we want to calculate the confidence interval of regression coefficient beta 1 in 3 methods, percentile, BC, and BCA. First, I create a matrix which consists of fish and copper density, like the homework this week. I extract the fish density and copper density from the raw data file, from the Excel file, and put them together into a matrix and generate 1,000 bootstrap samples and save these 1,000 samples into an empty array like this. And then I calculate the regression coefficient like this way in the last week homework, and the mean of beta 0 and beta 1 is 87.54 blah 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 and 0.1209 blah blah blah. First, the percentile methods. I arrange the 1,000 bootstrap beta 1s mentioned before into increasing order using the sort function. And I set the quantile limits of 95% confidence interval here, 0.025 and 0.975. And I'm going to select the value corresponding to this 95% confidence intervals quantile limits. So I select the 25th and 975th value from the arranged 1,000 bootstrap beta 1s, and the value is 0.0699 blah 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 to 0.1876 blah blah blah. This is the confidence interval produced by percentile method. Second, the BC methods, I use the ECDF function to generate an empirical CDF of bootstrap beta 1. And then I think I make the same mistake like Jason. I use the estimated mean to calculate the Z0, but it should be use the the mean of real data. The
regression coefficient of the real data should be the beta 1 of the real data.
Okay, beta 1. The beta 1 of real data and we get the corresponding cumulative probability from the empirical CDF corresponding to the observed beta 1 and get the Z0 from this cumulative probability. I use this Q-norm function to get the Z0. The Q-norm function is you give this function a cumulative probability. It returns the corresponding quantile value to you, and then calculate the 95% confidence interval boundaries, like this equation. And the result is the lower bound is 0.073 to blah blah blah, and the upper limit is the 0.198 blah blah blah. Third, the BCA methods. I calculate the jackknife beta 1s like this way and use the jackknife estimators to calculate the acceleration A value by this equation. And then calculate the boundary of 95% confidence interval. The Z0 in this equation is sent to which mentioned before in BC method, and the result is here. The lower limit is 0.065 blah blah blah, and the upper limit is 0.1853 blah blah blah. And going to question 2. In question 2, we want to test whether the density of two species is significant different. And first, I extract the density of the species OB and CP from the result of the first week homework, and put them together into a matrix and generate 1,000 paired bootstrap samples like the same way mentioned before. And here I calculate the difference between these two species, the bootstrap mean of these two species. In this question, my null hypothesis is OB. The mean of OB minus mean of CP is equal to 0, and the alternative hypothesis is the mean of OB minus mean of CP is not equal to 0. And then I calculate the difference between jackknife mean of these two species and use the bootstrap difference to calculate the Z0 value, and use the jackknife difference to calculate the acceleration value, and use this Z0 and acceleration to calculate the boundary of 95% confidence interval by BCA methods. And the result is the lower limit of 95% confidence interval is 36.222 blah blah blah, and the upper limit is 1037.966 blah blah blah. So in the So the 95% confidence interval doesn't include 0. It indicates that the mean of density of OV and CV are significantly different. And here is my conclusion about this week's homework. For the first question, the 95% confidence interval produced by 3 different methods is shown here. And for the question 2, my confidence interval doesn't include 0, and I reject my new hypothesis. The difference between density of 2 species is significantly different than 0.
Okay, thank you. Go back to the previous page. Okay, we have a 2 students have different It's question 2. Okay, actually I don't remember what the correct answer. But before we do that, let me go back to how you do a question 2 in terms of bootstrap. So the two you put it into a matrix.
Yep.
And then the bootstrap index is exactly the same for 2 species.
Yep.
Okay, that's again a typical mistake. So if the question is if two independent sample tests, like 2 samples should not sample in this pair. Right? So the index should be independent. So you are sample in pair. Because that 2 vectors share the same index. 他们用同样的 index， 我的理解是对的吗？
对，我让他们成对的错量。
So you cannot pair, right? Because you pair that because that's 2. We assume that 2 sample independent t-tests, right? So that should not be sample with pair, right? Otherwise it becomes pair. Okay. Okay. Thank you. Let me check the. Yeah, even. Maybe I can. Let's go back to another previous homework. This one. So how do you do for that question 2? Right, so for you do the independent bootstrap. You do the independent bootstrap， 你是2个不用同样的 index 嘛，对不对 ？Yeah, so that this one is correct. So he did the bootstrap for OV and then bootstrap for CP. So there's 2 independent bootstraps. So that's okay. Right, but I don't remember the correct answer. You guys figure it out. Okay. I do not remember reject or not reject your hypothesis. But apparently, this one is correct, okay? And then the next one is incorrect because it's sample is paired. It should not be sample is paired. In regression, if you're doing regression, the sample is paired. But if you do an independent two sample t-test, they should sample independent. They should not sample is paired. Is that okay? So 2 important messages for the homework for previous week. First, let me remind again. Okay, pay attention to the homework. But again, remind again, this, the beta 1, you put in, you calculate Z0, you should put in the observed beta 1, okay? Not the mean of all the bootstrap beta 1. Okay, that's the typical mistake. Okay, and then Second, the typical mistake is you forget to include observe the beta 1 in all the as one of your Bootstrap number. If you do not include observe the beta 1 as one of your Bootstrap number, then how can you know whether it's in the median or not? Right? It's impossible to know. So you must include the observe the beta 1 as one of your 1000 Bootstrap numbers. So you can find its location. Okay, that's the second key point for the previous homework. The third key point is that you need to understand whether you are doing the independent t-test or you're doing the paired t-test. Okay, the statistical meaning are different. Okay, all right. Any question for the homework last week? Okay. If not, then if you made a mistake, you still have a chance to correct your homework, all right? And you can submit the corrected homework, okay? All right. Okay, today we will talk about a completely different approach to do the hypothesis test. All right. So this is a lot. Again, uses some kind of random number concept, but this is a very different idea from previous topic. A lot of the computation procedure is kind of similar, but we are doing statistically very different things. Please read this paper, computation test for univariate or multivariate analysis of variance regression. Okay, because I am not able to explain all the detail of this paper, and please read this one. I will start with a very simple example of two independent sample t-test as an example to explain the concept of a computation test. Okay, or it is called randomization test. Suppose we draw a sample xi from a population, okay, and then we have two population. One is x1 and x2, and then you do the random sampling. You get the data of S11, 12, 13 to 1n, and then you get the second set of data from another second population, S21 to up to 2m. Okay, so because this is two sample t-test, then it's not necessarily equal to m, but it can be equal, so it's okay. Okay, but it does not. We do not require that sample sizes are the same for two independent t-tests. Suppose we are getting some kind of parameter. So typically we're asking the mean, right? So maybe the θ1 head is the mean for the first sample and the mean for the second sample. And the t-test, the new two-tailed t-test, the new hypothesis is θ1 equal to θ2, right? And that implies that the two distributions are the same. Okay, that implies the two distributions are the same. So if the null hypothesis is correct, if the null hypothesis is correct, that implies each sample data could have been drawn with equal probability from the other population. Okay, which means F1 is equal to F2, which means that two populations are not distinguishable. Okay, not distinguishable. So if so, I can draw from x1 or draw from s2, does not matter anymore because f1 is equal to f2, right? And θ1 is equal to θ2. That means I can pool all the data together and randomly divide it into m and example, right? Randomly pull all the data together and randomly divide it two parts, and calculate theta 1 and theta 2, and then calculate the difference between theta 1 and theta 2. The result will be the same. This doesn't matter, right? Because everybody belongs to the same. According to the null hypothesis, everybody belongs to the same distribution. Okay? So this suggests an alternative way to generate an expected distribution for theta 1 minus theta 2 is randomly assign group membership to each data. Okay? If this is true, if this null hypothesis is true, then theta 1 minus theta 2 is what? 0, right? It's 0. Right? 0. And then if you do the randomization, random shuffle all the data and generate again theta 1, theta 2 heads, then the difference is still 0. Still 0. Okay. Ideally, but not exactly. Ideally, but not exactly. So the idea, so the computation and the hypothesis test become extremely simple. Okay. What we really need to do is we generate randomize the version of theta 1 minus theta 2. I call it theta 1 head start minus theta 2 head start. I could call it delta start. Delta means difference. Okay. So that's the randomize the version of your delta. So you can do this 1,000 times, 10,000 times. So you generate and then you plot null distribution. It's called null distribution of your difference in mean. Right? Because you randomly assign membership, you randomly shuffle the two data sets, you expect the mean value of your delta is very close to 0, but not 100%, but very close to 0, right? Because I randomly shuffle it, and I calculate the difference in mean, right? So that means that you generate some kind of distribution, and that the distribution has a mean very close to 0. So that's trivial, right? That's trivial. Okay? So you generate this called a null distribution. Null distribution. Null distribution. Generate null distribution. Okay? And because why is it called null distribution? Because that's the distribution following exactly null hypothesis. Right? So that's the distribution of your difference in mean generated following null hypothesis. So it's called a null distribution. Okay? And then the hypothesis test become very easy. That is, now we can consider our observed difference in mean. Right? So we can calculate theta 1 head minus theta 2 head as observed difference in mean. And we can generate some kind of 95% confidence limit of your null distribution. Right? That is not this upper bound and lower bound. These are not confidence interval of difference in mean. These are confidence limit of your null distribution. Okay? And then we ask whether the theta 1, we look up where are we. So maybe your theta 1 minus theta 2 is here or here. Then we reject null hypothesis. Suppose it is two-tail test. Right? Of course, it's one-tail test, then you have to adjust whether it's an upper tail or lower tail. Right? If we observe the theta 1 minus theta 2 is here, somewhere between here, then you cannot reject null hypothesis. Right? It's okay? So this is super simple. Okay, this is super simple. But just keep in mind, you are going to do a one-tail or two-tail test, right? Because that limit differ. And if you're interested in the topic of this, all this topic for permutation test, there's a good textbook by Mandy, but it's all very old test. Okay. And they show simulation studies with random data that meet all the parametric assumptions have shown that achieve alpha level of the computation exact. Okay. And this is done without any assumption. This can be done without any assumption. You just need to know how to make the new distribution of your statistics. So you just need to write a computation code. No matter what the statistics is so complicated, no matter what, or follow the structure, follow the causal correlation structure, whatever we talked about last week. As long as you generate your new distribution, follow it, like satisfy all the data structure and like also satisfy new hypothesis, you can always generate new distribution of your theta or whatever, right? And make that new distribution of your statistics and do the hypothesis test. Okay? So in this case, you are always able to test your hypothesis, whether you reject or not reject your new hypothesis. Okay? But the limitation of this approach is that you are not able to calculate the confidence interval of your theta. Because in this procedure, we do not generate confidence interval of our theta, right? So this is very different from bootstrap, right? Bootstrap, so don't get confused, okay? Sometimes people get confused, so that will be the same. Remember, in the bootstrap, we calculate the theta, and then we calculate the confidence interval of theta, right? And then we ask the 95% confidence interval of theta include 0 or not, right? If you does not include 0, then we reject the hypothesis. Okay? But in this case, we do not generate the confidence interval of your theta. We generate the confidence limit of your new hypothesis. And then if I observe the data is beyond the new hypothesis, beyond the 95 confidence limit of the new hypothesis, then we reject the hypothesis. Okay? So the computation procedures seemingly kind of a bit confusing and almost the same, but the philosophical concept completely different. Alright? And in this case, because you are able to always find your observed theta, and you can compare your observed value with, you can rank, again, you can sort all the data, right? You can sort all the data from small to large. And then you can calculate exact p-value. You can calculate exact p-value. You can count how many new delta is larger than observed, right? And divide the total number of permutations. That's exact p-value. Okay, so compare randomization test. Sometimes I call it permutation test, I sometimes call it randomization test because in the test group that means the same thing. So the randomization test is sampling without replacement. Basically, randomly shuffle your data. Okay, randomly shuffle your data. And the bootstrap is sampling with replacement. Okay, so you can see in either case, they can generate a lot of number of randomization or a lot of number of bootstrap. Okay? Yeah, and then it does work. Okay? It's okay? So that's the fundamental concept for today, already finished. And then I'm going to give a various example of how to implement the randomization test in order to get a hypothesis test. Okay? So in the following example. You okay with the concept? Yeah? Okay. So the concept is actually much easier than bootstrap. Right? So this is a very popular approach to do the hypothesis test. Okay? But unfortunately, this method cannot give you confidence limit, which means this method cannot give you an estimate or uncertainty of your parameter. If you really want to get the uncertainty of parameter, you should use bootstrap. But if you don't care, you just need to decide whether you reject new hypothesis or not. Easiest way is to do the randomization test. It's even easier than bootstrap. Okay? Alright, and then let's talk about transformation. Remember, in the classical statistics, undergraduate statistics class, let's say, oh, because we need the data from Gaussian distribution, so sometimes we take a log transform, square root transform the data in a way so the data follow Gaussian distribution. But log transformation does not help because in the randomization test, we don't care about underlying distribution. And in any case, we can always generate a null distribution without transforming the data. So transformation of your original data has no meaning at all in terms of reject null hypothesis or not. Okay? So transformation to achieve normality has no value. Okay? And also sometimes the ideal statistics, the idea state can be simplified without any loss, called equivalence test statistics. Okay, then I'll talk about that example using the ANOVA, right? Power may be affected by the choice of statistics, but alpha is not affected. Okay. So that's typical statistics we are using. Say, for example, that theta 1 minus theta 2, that t-test, or the chi-square, right? Remember chi-square analysis, or independence, or chi-square test for goodness of fit. Okay, if you don't remember, chi-square test of goodness of fit, or chi-square test for independence, again, undergraduate testing. We'll give example also, or ANOVA. Okay. So just a remind, for regression and analysis of variance, if we have multiple variables, one dependent variable, two or more independent variables, and we have ANOVA, MANOVA, and so on. Okay, so that's the ANOVA. That's the formula for ANOVA, right? That's the formula for analysis of variance. So we have sum of square between, and then we calculate sum of square within, and then adjust degree of freedom. So we calculate the F ratio, right? And that's the degree of freedom, k minus 1 and minus k. And then you check the table, right? You check the table according to the degree of freedom. Check table where you always want to test. Where you observe the F is larger than the critical value of F. That's what you learned from undergrad, right? Okay. So we have to do all the process, and then we reject or don't reject your hypothesis. Okay, so that's the data typically looks like. We have different replicates, dependent samples, and then the three treatment ABC. So I have data A1, A2, blah blah blah, and B1, B2, C1, C2, and so on. And that's the total, and that's the typical number you need to do your ANOVA table. Okay. So in the classic ANOVA, you need to calculate F ratio, right? So that's the F ratio. That's your test statistics F. However, in the randomization test, you are going to generate your own sort of F distribution. The intuitive way to do the randomization test for ANOVA is that I'm going to just randomly shuffle that data, right? Because following null hypothesis, the result of treatment A, B, C is the same, right? So I can randomly shuffle the data this way. I randomly shuffle the data this way, and do repeatedly calculate F 1,000 times. So you generate a null distribution of F, right? So in this case, you generate your own null distribution of F. So you forget about the table developed by Fisher. You don't care about the Fisher anymore because you can generate the F distribution on your own, right, using computation. So you just need to compare your observed F versus your null distribution of F, and you're done. Okay? So that's a simple-minded way to do that F test. But in reality, you do not need to calculate F all the time. You do not need to calculate F. This is called equivalence test. The reason is first, because the degree of freedom are constant for all of the population. No matter how you do that, these are constant. So F is approximated by this value. But you don't need to divide it, you don't need to take care of degree of freedom, right, when you generate a new distribution. Okay? Because the statistically is just a transform. The transformation divided by constant does not have an effect, right? And also, by definition, we know SST is SSB plus SSW, and this is, again, constant for all the commutation. So in order to test the new distribution of this, you don't really need to do that, you just need to do that. Generate new distribution of SSB, because SSB plus SSW always constant. Okay? And how to calculate SSB? This formula. And because this is, again, always constant for all the permutation, you just need to calculate this. Just need to calculate this. So to do the equivalent ANOVA test, this becomes computationally extremely easy. All you need to do is calculate this number, right? All you need to do is calculate this number. Okay, very easy. All you need to do is calculate this number, and then randomly shuffle and repeatedly calculate the permutated version of this number, the generate new distribution, and compare your observed with your permuted this new distribution. Right, so you don't need all this formula to do the ANOVA. All you need to do is compute this number, then the new distribution of this number. Super easy. Right? Because we do not need to work very hard to make our statistics following F distribution. Right? The reason we should do that is because he needs to prove this number will approach or follow F distribution. Right? But we no longer need the F distribution anymore because we can generate our own new distribution. So all you need to do is do this for your ANOVA. Okay? Very fast. Okay, so keep this in mind for any hypothesis test. You can make it really efficient. However, we know the computer are very fast. If you don't mind, you don't care, you can call the built-in F function 1,000 times. The result will be the same. Okay, if you don't want to do this by yourself, you just need to call randomize the data and call your F function 1,000 times. That would be okay. That's also okay. But it just a lot of computation time wasted. Okay, so in the following, I'm going to follow up, give more example. Okay, so we talk about ANOVA F test. This example is for randomization test for chi-square. Okay, chi-square. So these are some kind of very typical data for sort of population genetics. Okay, population genetics. So someone collect the genetic data. So it's a mitochondria DNA haplotype data. Okay, there are several haplotypes, and they are going to 2 regions, and I get a data like that. Okay. And then my question is that whether the haplotype differ between the 2 regions. Okay, differ between the 2 regions. Okay, so that's the total sample size. Okay, that's different haplotype, and that's 2 regions. So if we do the classic statistics textbook way, we are doing that chi-square distribution, right? We need to calculate chi-square distribution. How to calculate chi-square? All is observed, E is expected, E is expected, and then degree of freedom is n minus 1 multiplied with n minus 1. So n is the that's the number of column, number of row and number of column. Okay, number of row and number of column. So basically, so this is observed data, right? This is observed data, and what is expected number? How to calculate expected number? How to calculate expected number, kids? Chi-square test for independency. Chi-square test for independency. How to calculate expected number? So this is observed. Everybody knows how to get the expected number. You know? Don't remember? Anyone? How to get the expected number? Okay. So this is the low sum, 23, right? This is the current sum, is 19. Total number is 45. If that table is independent, in terms of probability, the probability of this will be 23 divided by 45, right? That's pi. So pj 19, sorry. Divided by 45. Okay? And then what's the probability of this? Bij. If it current and low, if this generated by the random data generated by is total independence. Bij is what? Sorry, this does not work. For independence, Bij equals to Pi times Pj. By the probability of this cell, Pi minus Pj. So what is E? What is the Aij? Aij will be the total number 45 multiplied with Pij. It's okay? So every cell calculation following this formula. It's okay? That is expected number. That expected number assuming dependency. Okay? So the very easy is actually for this E11 is actually 45 multiplied with this number multiplied with this number. Okay? So this cancel out, right? So this number multiplied and divided by 45. Okay? So these are cancel out, right? So that will be this number. So it will be this number multiplied with this number divided by 45. That's the expected number for this. Right? And for this one, again, so that's this number multiplied with this number divided by 45. Right? For this one will be this divided by 45. That's the expected number for every step. Can be calculated this way. It's okay? Even that's following the null hypothesis, like independence. Okay, independence. Alright? And so you get your chi-square, right? Because you always have this, and then not following chi-square, distribution and that degree of freedom, and you check chi-square table. Chi-square test always one tail. Right? Is it okay? If you don't remember, again, that's in your undergraduate statistics textbook. Okay? Test for independence. Okay, n by n contingency table. We call it contingency table test. However, that for chi-square distribution, the necessary requirement is that each over Eij must be bigger than 5. Okay, any cell, not Oij, okay, Eij, any cell or any cell of the Eij, necessary condition for the chi-square test to work is that Eij must bigger than 5 for each cell. Okay? Otherwise, the data would not follow chi-square distribution, and therefore, the chi-square test does not work. Right? Yeah, again, that's an undergraduate textbook. However, as you can imagine, in this data set, many cells cannot possibly have their Eij bigger than 5. It's impossible following the data distribution. If you encounter this kind of genetic data, it's actually very commonly observed that chi-square, typical chi-square test, the classic chi-square test for the population genetic question does not work. Okay, does not work because it violates the assumption. So the simple way to do this is that we forget about chi-square distribution. We forget about chi-square distribution. We are going to generate our own chi-square new distribution of chi-square numbers, of chi-square value. So you randomly shuffle your data set. You randomly shuffle your data set and generate a new distribution of your chi-square. And then compare your observed versus new distribution of chi-square. Then you do not require that assumption. Right? Because you no longer check the chi-square table, you check your own new distribution of chi-square. So how you do the procedure? So you randomly assign each individual into region 1 or 2. That's your data. That's your data. So that's your sample size, right? That's your sample size. Like when you collect the sample from 1 individuals, you can get their genetic data, right? You can get their haplotype data, right? So what you really need to do is that totally now you have 45 samples. You mix them and you divide it again into 2 groups, 90 and 26. But randomly. When you do this, you can then recollect their data, right? If you basically randomly shuffle individuals, and then you recollect the data, so you generate a randomized this table, after randomizing the individuals. It's okay? So for every time you randomize that individual, you can always again generate this kind of data following new distribution. And you have randomized the version of this data set, you calculate the chi-square again. That is a new distribution of the chi-square. Okay? And then you observe the distribution of chi-square. Okay? So you can create a new distribution and then compare that actual chi-square value to this new distribution, and then chi-square is always 1 tail. Okay, so that's your new distribution of chi-square, and then you observe that the chi-square number is here, then you reject the hypothesis. It's cool? Okay? No? Yes? Yes? Okay. And that is exactly the software, usually some commercial software is doing for you. Okay, and then I like to talk about testing the procedure of your randomization test design. Okay, because keep in mind, in a very simple example, we talk about ANOVA chi-square. That sampling design is very simple. It's very simple. Suppose we have a very complicated sampling design, and then we want to carry out randomization test. But you are not 100% confident whether your randomization procedure is correct or not. Okay? Then you can generate some kind of test procedure for your randomization test. It's okay? So you first, if you use randomization, your random shuffle program is very complicated because your data are very complicated structure. You might want to test whether the randomization procedure is correct. Okay, is correct before you apply the randomization procedure into your real-world data. So that's called testing procedure for randomization design. Okay. So how can you do that? You need to generate a large sample from the one single distribution. You can decide maybe generate from Gaussian or generate from uniform. It's up to you, depending on your research question, depending on your design. Anyway, you generate a sample from one distribution. Okay? So for example, I'm going to test whether my randomization design for t-test is correct or for ANOVA is useful, effective or not. Okay? So I can say subsample randomly with realistic sample size. In the ANOVA, I may subsample 3 data sets from one big randomly generated population, and I choose 3 randomly select. Right? It's randomly selected, right? Because then actually 1, 2, 3, the 3 data sets are actually the same. But anyway, because you just want to test the procedure. Okay. And this example, say this example actually is this example. This example, okay, this one. So let's say I subsample randomly with this sample size, and then I assign individuals to each region at random, and I do a randomization test. Okay, and I repeat many times and check the distribution of p-value. Because they are actually the data is not structured. No matter how you subsample and randomly assign, you cannot reject. You can generate all kind of results. Okay, all kind of possible results. So if a randomization procedure is correct, p-value should follow uniform distribution. P-value always between 0 and 1, right? And then you do repeat it many times. If you repeat it many times, by chance, p-value is smaller than 0.05. By chance, p-value is 0.1. By chance, p-value is 0.2. By chance, p-value is going 3. Because everything is by chance. Okay, so p-value can be anywhere between 0 and 1. And if you generate 10,000 p-values, all these 10,000 generated p-value following the procedure should follow uniform distribution. Okay? It's okay, so that's a procedure. Test your procedure. Okay, and then I have again several examples to explain before we take a break. So it's also very popular, something called a Mentel's test. You might heard about it, Mentel's test. So Mentel's test is used to compare two metrics. In this example, I'll calculate the genetic distance between locations. So I have 4 sampling sites. For A12 is the genetic distance between psi 1 and psi 2, and so on and so forth. Right? I can calculate the genetic distance between pairwise location. And again, for this number, this is symmetrical, right? A12 is A21, A2, because that's distance. Okay? And then for the matrix B, I'll calculate the physical distance between the location, the sampling site, geographical distance. Okay, the real distance of the two sampling sites. Okay? And my question is that genetic distance related to the physical distance. Right, so this is called isolation by distance from genetics. If two sites very far apart, the genetic distance is expected to be larger. Right? If the two sites close, the genetic distance is expected to be smaller. Right? And if that is the case, it's called isolation by distance, assuming that the two sides are very far apart. The dispersal is more difficult, migration is more limited. If the two sides are very close, the dispersal is very frequent, and therefore genetic data are very similar. It's called isolation by distance. So this is a very commonly asked question in population genetics. Okay? So the question is the genetic distance related to physical distance. So I need to do the correlation between this matrix versus this matrix. Right? Okay? And then I can then calculate the correlation coefficient of this versus this data set. Very simple calculation. Right? Very simple calculation. And then how can I decide whether that correlation coefficient is called Mendel's correlation? Is that I randomly shuffle the data. Okay, I randomly shuffle the data and repeatedly calculate up. Right? So it becomes easy. So you randomly scramble the element of one matrix. Okay, only one set of diagonal. So you just randomly shuffle these numbers. It's good enough. Of course, if you like, you can shuffle it too, but it just does not help, right? As long as you shuffle one set, it's good enough. You can shuffle both sets, but totally fine. Yeah, but you just need to shuffle one set. And then you can repeatedly calculate the R, and then compare the true statistics to the random distribution. Okay, so that's how the Mendel's R is tested against no hypothesis. Is okay? Getting slightly more complicated. The concept is the same. So it is called analysis of molecular variance, AMOVA. Okay, so it's test the genetic distance between areas. So that's 3 areas. So you have many sample individuals. You get the DNA data like that. Okay, and then you can calculate the genetic distance between area 1 and 2, 2 and 3, and 1 and 3, and so on. Right? So that's genetic distance. Pairwise genetic distance. And the question is that if it is observed the total genetic distance larger than could be anticipated by chance alone. Whether the question is whether there is genetic differentiation among 3 areas. Okay, the question is asked whether there is a genetic differentiation among 3 areas. Okay, so what I do is I calculate the pairwise genetic distance. And I calculate total genetic distance. Total genetic distance. Okay? And what I mean by anticipated by chance alone, that is simply you just random shuffle your data set and then repeatedly calculate your total genetic distance. So what you do is that you randomly assign the area tagged to each sample. You randomly assign the area tagged to each sample, and you repeat, and you calculate no distribution of summation D. That is your no distribution. Okay? And then you can ask whether that observed summation D is different from your null distribution of summation D. Okay, test of AMOVA. If you cannot reject null hypothesis, then there is no genetic differentiation among three areas. Okay, we can commonly ask questions. All right. Before I talk about nested AMOVA, I'm going to take a break. Okay, and I'll come back at 10:50 and talk about more complicated randomization procedure. Right. suppose I have a nested ANOVA design. I'm testing something. I've designed, I have two sampling locations. And within sampling locations, I have a site. So maybe site A, treatment A, treatment B, treatment C. And here also treatment A, treatment B, treatment C. Okay, something like that. So you have maybe structured design of your ANOVA, then that's nested. So then you need to be careful about how you random shuffle your data, because it depends on your null hypothesis, depending on the question you are asking. Suppose we are asked whether the treatment ABC is different, okay, whether treatment has effects, we should maintain the structure of two locations, location 1 and location 2. You just shuffle the data between or among the three sites. Okay, three treatments. Okay, you random shuffle that way. And then you random shuffle that. You don't want to shuffle something here to here, because this location itself has effect. Okay, location generates variance, right? So you don't want to shuffle between location, because now your question is whether the site has effect. Okay, you just shuffle this way and then this way. Alright? If your question is to ask whether the location has effect, then you should shuffle the site between the location. You don't want to destroy that. You don't want to destroy that structure. You shuffle the whole site. Site is your unit for shuffle. Okay? Because you are asking whether location 1 differs from location 2. Is okay? So depending on your research questions, you need to carefully decide how you're going to shuffle. So what's your unit of shuffling? Right? And that generates null hypothesis, and the test is extremely simple. If you do the classic nested ANOVA, you need to generate the ANOVA table as a nested structure. Right? You have a variation partitioning. And you have variation contributed by two locations, and contributed by site within the location, and contributed by quadrant within the site. So it's nested. Right? The hypothesis test become slightly more complicated. Degree of freedom you adjust depending on your hypothesis test. Okay, maybe in the undergraduate you don't even learn how to do the nested ANOVA analysis. Typically, in the experimental design textbook, you learn how to do nested ANOVA. But it's okay. Today we explain how you can do the randomization test for nested ANOVA without even calculate the nested structural variance. Right? We don't need to calculate the variance for each component, because we just want to reject or do not reject null hypothesis. You just need to generate null distribution. Okay? So test your nested ANOVA. Right? So that's some more detailed procedure. Please read that paper. Okay, regression. So I have a y variable, x1 and x2, and I have data like that. So I can do a regression analysis, right? So you can calculate the beta 0, beta 1, beta 2, right? And then you can calculate standard error beta 1, beta 2, right? And then you can test it. You can do the global F test, right? Global F test, or you can do the T test for each beta 1, beta 2. So that's classic way to the multivariate linear regression. Right? If you don't remember, again, that's your textbook. Right now, we are going to explain the randomization version of a linear regression analysis. Very easy. I just randomly shuffle yi and x, and then calculate the beta many times, and make comparison, right? Very easy. Okay, very easy. Intuitively, very easy. Just randomly shuffle. However, the question is that how how to shuffle, how to randomize. Shall we randomize this? Or shall we randomize this? Or shall we randomize this? Or randomize everything? Right? So that's a question. That's a decision we have to make. We have to make depending on our research question and depending on our data structure. Okay? So suppose, details here and more detail in the paper, but I just give some examples. A very simple example, if x1 and x2 are two independent variables, okay? x1 and x2 are two independent variables, and y is a response variable. Then I just need to randomize this one and this one independently, because x1 and x2 are independent. So if I like to test the regression coefficient, I generate two distribution of beta 0 and beta 1 and beta 2. I randomize this one and randomize this one independently because x1 and x2 are independent. Okay, and y is dependent variable. So you don't want to, you keep this, you just randomize this and randomize this independent. It's okay? Yeah? Okay. Now, if x1 and x2 are correlated, for example, y1 is your blood pressure, okay? And then say x1 is your body weight, x2 is your body height. My question is very simple, is whether your blood pressure is related to your body weight. That's my research question. Okay, but we also know already from medical data, your blood pressure also depending on your body height, hypothetically, right? The question is asked whether x1 is correlated with, has a significant relationship with y1, but not conditionally on s2, because x1 and s2 are not independent variables. Two are correlated. You are tall, of course, you have higher body weight, right? So S1 and S2 are not independent. But I'm asking the relationship between Y and X1. So in this case, I keep the Y, I keep the X2, because I believe body height also, blood pressure related body height. Okay, hypothetically. Okay, but I'm asking whether the body weight has positive effect on blood pressure. So I keep this, I randomize this. Okay? That's the second case. Right. The third case, if S1 and S2 I'm sorry, I made a mistake. Body weight and body height are correlated with Y1. So they are correlated, okay, they need to be always in pair. So sorry I take it back. Second example. Body weight and body height are always in pair because that person has body weight and body height. Okay, I'm asking the blood pressure effect related. Blood pressure result related to body weight, body height. So this should be always paired. You don't want to shuffle this. You shuffle this one. Okay, shuffle this one. Sorry, I gave a wrong example. Okay, so that's the second case. The third case is that this is your body weight. This is blood pressure. And that's the dose of your medicine. You take some medicine in order to control your blood pressure. But we also know the blood pressure is depending on your body weight. So this is body weight, that's blood pressure, that's the medicine treatment. Okay? I'm asking whether the medicine treatment has effects on the body pressure, blood pressure. Okay? In this case, I only shuffle the treatment because that person always has that weight. Okay, so weight, body pressure, blood pressure, so be paired, and I randomly shuffle those. Okay, so even with this very simple setting, I have one dependent variable, two independent variable. How to shuffle depending on your research question and the research design. If S1 and S2 are independent, and these are not, and then just randomly shuffle this one and also this one. Okay. And if S1 and S2 are closely linked, they are related, and you keep this and shuffle this one. Okay. And if Y and X2 these are linked, so these are body weights, blood pressure, you shuffle this one. Okay. So that's critical because how you random shuffle in the more complicated multilinear regression case, how you shuffle creates a very different null hypothesis. Alright, how you shuffle decide the null hypothesis. Okay, so different null hypothesis, different design will lead to different shuffle. Right? I said this already. Okay, and then another more complicated case is called a partial correlation. I have a multivariate question like that. So Y is growth of bivalve, and X is a temperature, and Z is a particular organic matter. So temperature influences growth, right? Because we know higher temperature increase growth rate. A particular organic matter is a food for bivalve. A higher food concentration, the growth rate is higher. Okay. And more complicated in the ocean, PLM concentration is related to temperature also. Okay, because it's oceanography. Okay. So all three are related. We know by knowledge. However, in a real world situation, we collect data, we want to ask, is there a relationship between growth of bivalve and PLM given given effect of temperature, conditional on temperature? So this is called a partial correlation. Okay, so I ask whether Y has a relationship with Z conditionally on X. Conditionally on X. Okay. So the idea is you after accounting for effect of X, and you calculate the residual correlation between Y and Z. However, complicated things is Z also depends on X. Z depends on X, Y also depends on X. You ask under this condition, you ask the relationship between Y and Z. Okay? So in a classical way to calculate the partial correlation is this way. Okay, is this way. So the effect of temperature must be removed before testing growth versus POA. So the effect of temperature needs to be removed from growth rate, also removed from POA. So that's the definition of partial correlation. Okay, that's the definition of partial correlation. Alright? Now, of course, this is a classical way. Okay, this is a classical way to calculate partial correlation. And then how you generate a random distribution, how you randomize, how you generate new distribution for testing beta 2. We are interested in beta 2 only. Okay, we are interested in beta 2 in this case. We are only interested in beta 2, conditionally on X variable. Alright? So there are three possible ways to do the hypothesis test. Very simple way is to permute Y and keep X and Z fixed. Because we believe Z conditional on X. Because we believe Z conditional on X, right? According to our knowledge. So we keep X and Z, and we randomly shuffle only Y. Okay? That is called a permutation of raw data. Permutation of raw data. Again, the null hypothesis is beta 2 is equal to 0 according to beta 2. Okay, simple way, easiest way to permute only one. Okay? And then second way is to permute residual under reduced model. What is reduced model? Reduced model is you do the regression for this one. You do the regression for this first, you do this regression. First, without considering z. Okay? And that regression is investigating the relationship between y and x. Right? And then you get the B0 and B1 right from your data without considering this. And you get a residual. You get a residual. And that is a residual. And you get a residual, so the residual is already removed effect of x, right? So that's a remaining effect. Then you shuffle, you permute the residual against z given x. So basically, you generally permute the residual and put it back. Put it back. Okay, put it back. Okay, and then you recalculate the result. Calculate the result. Okay, so this is called a permutation for reduced model. And this one is called a permutation under full model. Basically, I calculate the full model. I estimate the beta 0. I estimate the beta 0 as B0, B1, B2. Okay, so let's put everything in. But now we get the residual of y given xz. Okay, and then you permute the residuals against z given x. Okay, this is called a permutation of residual under full model. Okay, under full model. Okay, so either the A, B, C three types, they all make sense. They all make sense. However, you can imagine that result could be quite different. Can be quite different because all these cases are under some different kind of assumption of your data structure. But all these cases can make sense. They can make sense. Okay? And then the recommendation. Okay, there's a recommendation. Typically, that the middle part permute the residual under this model is the optimal solution. Okay, this is the optimal solution. So this one, the blue one, this will be the best solution to do that partial regression analysis. So it's a reduce the model. Okay? All right. We talk about ANOVA, chi-square regression, and then I talk a little bit on MANOVA. MANOVA is a multivariate analysis of variance. So for the ANOVA, we have only one dependent variable, but for MANOVA, we have more than one dependent variable. Okay, in this case, the effect of varietal treatment on corn production. So that's a varietal treatment, different concentration over S1, S2, S3. And for your output, your Y, you can measure the yield, or you can measure the time to mature. So you have two dependent variables, and we want to consider two dependent variables. We can individually, we can do this analysis and do this analysis independently. Then we have two set of ANOVA, right? Two independent ANOVA tests. That's a simple way. But we are interested in more than one. We want to consider everything together. Okay, we want to consider Y1 and Y2 together with respect to your treatment. Then we have a multivariate analysis of variance. Okay. Right, I can write it into some matrix formula. Okay. So it is a multivariate general linear hypothesis, and you can use some building function. Okay, in that R package, and then you can use independently ANOVA, and then combine them to have a joint statistics. For the randomization version, again, also we can do that all at once, or we can do it separately and combine it. It's better to do it at once. It is better to do it at once. Okay. This is very simple. You just do the MANOVA and you run the shuffle, and then ANOVA, repeat it again. The same as ANOVA, repeat it again. You can call the building function and shuffle the data and repeatedly call the building function. That's the easiest way if you don't want to spend time to figure out what is the equivalence test. Okay. Or you can do the univariate and then use the composite measure. So you randomize y1 and estimate the beta1 and f1, or y2 you estimate f2, and then you calculate composite, sum them, or take a log and sum them does some equivalently, and you randomize. Okay. Either way, you need to randomize, but you can do it all at once, or you can do it separately, but two univariate. But as I said, this one is recommended. Just keep in mind, if you choose to do this, if you choose to do this way, if you choose to do this way, you need to be careful. Because for each univariate F ratio, we can compute like t value of beta, right? That's the classical way. And then we composite them. You might sum them, right? You might sum them, okay? Or you take a log this, or you take a log, you sum them, all right? However, in this case, if your y1 increase with S1, but the y2 decrease S1, then beta 1, beta 1, 2 tend to have opposite side. Okay, then you sum them, become 0, become more confused. So in this case, you want to take that absolute value and then sum them. Okay, just be careful if you choose this way. Okay, choose this way. But as I said, recommended, it's easier to do this way. Okay, it's better to do this way. And then randomization test is very flexible. You just be really careful about your new hypothesis, your research question, and your new hypothesis, how you randomize them. Okay. So people can invent their own randomization test. So this is a method I invented many years ago. I have a data like that. So that's a location of some centroid. So I have a fish data collected around the area. And every year, I can calculate the centroid of a distribution of that fish population. Okay, so maybe this year, don't care, at this moment we don't care about the size of the symbol. The size of the symbol represents abundance. Okay, but here we only care about the location. So I have two climate condition. I have two climate condition, triangle and circle. If the water temperature is warmer, then they tend to have a triangle distribution. Okay, maybe the distribution may be around here. If the temperature is lower, temperature is lower, in the cold climate, they tend to have a southern distribution. Okay, it's kind of, I can see that visibly, but I'd like to test whether is there a difference in the distribution domain in the two climate periods. Okay, so that's a procedure like that. So that's maybe the data distribution like this. So that's the 2D, two-dimensional, that's space, right? And then latitude, longitude. So for the warmer period, you have triangle for many years, triangle like that. And for many years in cold period, you have a circle like that. Of course, you can calculate the centroid for all the circle and centroid for all the triangle. You find, well, maybe change the distribution. Okay, on average. Then the question is whether that change or whether the shift in terms of the geographical distribution is significant or not. Is significant. When I say significant, I need to, significant different from random, right? So the test to test the shift in distribution domain very easy. You can design some kind of abnormal type of a randomization test. You first calculate all the pairwise distance within the circle. Okay. You then calculate all the pairwise distance between. Within. So all the pairwise distance between the circle. Okay, within the domain, right? So all the pairwise between circle, and all the pairwise between triangle. Okay. So actually, that's the variance within circle and variance, sort of estimate of variance within triangle and variance within circle. You can then take some average of all the pairwise distance within and all the pairwise distance within. And then you calculate all the pairwise distance between triangle and the circle, all the pairwise distance between triangle and the circle, all the pairwise. Okay? And if there's no difference, and you then calculate the ratio between this and versus this. Right? So this is very like ANOVA. So the variance within, variance between. If variance between is larger, if you calculate the ratio of these two, if the ratio is large, which means the variance between is large, which means that the distance between triangle and circle are very large. Okay? Very large. And then you just randomize, assign a group. So make it this triangle, make it this circle, you randomly assign. So you randomly assign the climate regime for each year, actually each data point. And then again you calculate this, then you repeat it. Okay? So I repeat again, so we compute the sum of all or average, whatever, is equivalent, right? So you can calculate the sum of all pairwise distance between distribution center within period 1 and within period 2. Okay, so that is the distance, pairwise distance within, right? Is similar as a variance within, right? It's similar as a variance within for ANOVA. But here is a distance, pairwise distance within, Okay? And then we calculate pairwise distance between. Okay, pairwise distance between. Okay, so you create the statistics. T is equal to W divided by B. Okay, and then if this T is small, if the T is small, which means B is large, right? If B is large, the pairwise distance between the two periods is large, right? Which means they are separate, right? And then you randomize. You randomize the data set and create a new distribution of T, and then you can do the hypothesis test. Okay, it's a very simple concept. So likewise, you can design whatever your randomization test, okay, for your interest. All right. So the advantage of randomization. Randomization tests do not require random sampling, rather they require random reassignment in samples. Okay? And in order to generate new distribution. However, keep in mind, if you want to generate random assignment, you still need a random sampling, you need data. If you have no data, if the data do not randomly sampled, then of course the randomization of your data does not make sense. Still, random sampling is required as a fundamental step for your data collection. Okay. So randomization tests are no substitute for random sampling. Okay, but it has an advantage, that is that you do not require the data follow any distribution. Because in any case, you are able to generate your null hypothesis. Generate your null distribution following your null hypothesis. Okay? So it's versatile. So researchers can develop their own test. Right? So for example, I developed my own test for the shift of the distribution regime. Okay? And easy to understand, right? Actually, who invented the validation test? Actually, Fisher invented the validation test. But Fisher was not able to do the validation test because he had no computer. Okay? Because at that time, there's no computer to do this computer-intensive statistics. So Fisher has to work very hard to create a statistic distribution, assuming the data follow Gaussian, he created F distribution, and so on and so forth. If he has computer, then he does not have to do the mathematics. It does not have to invent F distribution if he can generate a null distribution. So he actually said that, but he cannot do that. So he has to develop F test. All right. Final topic before we start is called the Monte Carlo test. Okay, Monte Carlo test. A kind of randomization. But previously, when the randomization test, we randomize the data to create null distribution. Okay, so Monte Carlo test is a parametric randomization test. Parametric version of randomization test. If you have some belief, your data following some specific distribution, you can generate the random numbers from your null hypothesis from your expected distribution. Okay, and then compare your observed statistics with your generated null distribution and make a hypothesis test. It's easier to make an example. So this is in the forest, ecology, 101, you learn this. That's called the nearest neighbor test using Monte Carlo. So each point indicates location of each individual tree. And then it looks like random on the sampling space, two-dimensional sampling site. It looks superficially, it looks like random. Okay? But the question is it really random, distributed everywhere, anywhere? Okay? So, we are interested in the distance between trees. We are interested in distance between trees. For each individual target tree, I can calculate the nearest neighbor. Distance for the nearest neighbor for each individual tree. So this one is here, this one here, and this one here. And then I take an average. Of course, I can then calculate G2 is the average of the second nearest, and then the third nearest, and so on and so forth. I can calculate G1, G2, G3, so on and so forth. Okay? So I can generate a distribution from your real-world data as squared as real-world data. The distribution of your G1, G2, G3. Okay? G1 is G1, so on and so forth. Right? That's from your observed data. And then, what is the null for G1, G2, G3? The hypothesis is that if the trees are totally 71 trees, so if there's no interaction between tree individuals, supposedly, All right, and then suppose the environment is homogeneous, so the tree can grow anywhere on that space, right? So you just need to generate a uniform distribution of x and uniform distribution of y, because the tree can grow anywhere here, anywhere there, right? Anywhere, homogeneous probability. Okay? So you just generate for every tree individual, you can grow the tree, you can plant the tree following this very simple two-dimensional uniform distribution. Right? That assumes the tree can grow anywhere. Doesn't care about other trees. Right? Doesn't care about environmental variability. So you can generate again, many times. You can plant 71 trees again, and then you repeatedly calculate G1, G2 from all these randomly generated. This is a parametric random sampling, right? Assuming that follow uniform distribution. They can grow anywhere on space. So you repeatedly do that 1,000 times, and then you can then calculate 95 confidence bands of your G1, G2, G3, G1, and so on. Right? It's easy to do. Then you can compare your observed G1, G2 versus your confidence band of your randomized G1, G2. So you realize actually that real world data, this is a typical example in a textbook. You realize the G1 is outside of your confidence band. The G1, the nearest neighbor distance is larger than expected by random. G2 also might not be young. Okay, so that suggests, this is the classical interpretation. That is that three individuals, in order to avoid competition with other individuals, so they are further apart than expected by random. Okay? And then for the second is slightly, but then if that further, the third nearest tree, I don't care, because in any way we have to pick this somewhere in the space. So I don't care. I only care the nearest tree and second nearest tree, because we are competing the resource. That's a classic interpretation, but this is certainly not true, because in real world situation, the environment is very complicated. And in reality, the tree have different species. Like maybe some tree competed with other tree species, or some within species competition, between species competition, and so on. Okay? So this is the simplest test, simple-minded test for Monte Carlo demonstration in the textbook. Right? But keep in mind, in reality, it's more complicated. In reality, when you do the randomization, you need to make a circle. Right? You need to make a circle, and then because that circle represents environmental heterogeneity, and then you have to also consider species. Right? So you have a much more complicated way of generating null hypothesis. Okay, in 10 years ago, I have a master's student doing that. Yeah, but that basically that question already solved. Right? So people now understand how to generate correct null hypothesis, considering the tree species, considering the environmental heterogeneity. If you're interested, you can look into literature. But this is the simplest way. Okay. But in any case, that's following a framework of Monte Carlo. Okay, Monte Carlo generation for Monte Carlo test for your statistics. So this is a parametric version of a randomization test. Okay. All right. So let's come to the end of the lecture for today. The homework kind of familiar. Again, fish, copperpot regression, right? And then instead of doing the bootstrap confidence interval, you're going to make a randomization test to generate null distribution of beta 1 and test whether beta 1 is significantly different from null distribution 5,000 times. Okay? To caution, in this case, we no longer sample with pair, right? Because we are going to generate a randomized version. Okay, so you can randomize this or can randomize this. Of course, you can randomize both, but it will steal your time. Okay, you just need to generate one variables, and then create a new distribution of beta 1, right? And then you have new distribution of beta 1, you compare your observed beta 1. So now your observed beta 1 is not part of your randomized beta 1, right? Different from bootstrapping. Okay, so observed and 5,000 randomized, right? 5,000 randomized. And then you can then compare how many randomized beta 1 include observed beta 1, right? You can then, if observed the beta 1 is significantly larger than any of the 5,000 numbers, what is the p-value? What is the p-value? P-value will be, you have 5,000 randomized, the p-value will be smaller than 1 by 5,000, right? If observed beta 1 is outside any of this distribution, a p-value is this, right? And p-value, if that among the 5,000 times, if the two randomized beta 1 is bigger than your observed beta 1, then p-value is exact, right? Exact. So exact. It's exact. Okay. So the advantage of the randomization test, you can always get exact p-value. You can always get exact p-value depending on how many times, right? And the tricky part, what is the smallest p-value you can get from your randomization test? Depending on number of randomization, right? If you have 1,000 randomization, the smallest will be p minus 1 divided by 1,000. If you have 10,000, the p-value becomes smaller. If you have 100,000 p-value, so the p-value can be made arbitrarily small by increasing number of permutation. Okay? If you really want to say your hypothesis test is rejected and then the p-value is very, very small, then you really need to increase your number of randomization. You can make it arbitrarily small. Of course, not really arbitrary, because if you run the too many times, always in the end, p-value is exact, right? P-value becomes exact. Okay? So you will report your p-value. Okay? Can be exact or smaller than 1 divided by 5,000. Okay? That's how we calculate your p-value. Right? You just need to count how many times that new beta 1 is larger than observed beta 1. Right? And then likewise, for the question 2 for independent two-sample test, t-test, again, you calculate difference in mean and then you randomize. Okay, randomize. In this case, when you say randomize, you pool all the data and randomize divided into parts, right? And then you can again generate your difference in mean. And then you need to report your p-value. Alright? Report your p-value. And keep in mind, this is the two-tail test. Same question, the two-tail t-test. So you need to think about in the two-tail test how to calculate exact p-value. Okay? Okay. Again, you write your own randomization routine. I'm sure you already know how to do that in second homework, right? Okay, that's all. Homework presentation. Raise your hand. Okay, good. 2. This one should be easy. Any question? Any question for previous homework or the lecture for today? Okay, if not, then we'll stop here. All right, I'll see you next week.